For those who do not know what a copula is, let us try to think about the following. Let's say we want to create a model for a bivariate distribution. Okay, both marginals are uniform, should be uniform, and they should be correlated with correlation, say half. Okay, so how would we do that? Okay, some context we want. Bivariate, both marginals x and y, let's say, uniform. They should be correlated, correlation half, and nothing more is at the moment specified. Okay, so I'll first describe you a model which you can immediately see that in most realistic context this will be a useless model. One model could be, you take with probability half, our random variables are independent uniforms, and with probability half it is just one uniform random variable u comma u. So u and v are two independent uniforms, and my x and y is with probability half, x is equal to u and y is equal to v with probability half, and with the remaining probability half, x and y both are equal to u. Okay. Now you can easily see that both the marginals will be uniform, because with this conditioning event is independent of these uniforms if you take that. Okay, but this will be a ridiculous model. I mean, we want these two u to be uniform, but I mean to be correlated with half, but it is not that with probability half they are independent and with probability half they are exactly equal. No realistic scenario we will come up with such a situation. Of course, but I did not specify any more conditions in my description. So this also fits, but if you are trying to model some phenomena, you will still may not like to use this. Now, what are the other alternatives? Well, one alternative is the following. We know how to construct bivariate normal with given correlations. Right? So let's start with x and y bivariate normal with correlation half. Now you also know that if you compose the distribution function and any random variable and its distribution function. So x a random variable, f is its distribution function, then f of x has what distribution? Uniform. If x is continuous, then f of x will have a uniform distribution. So let's try to use this fact. Take x and y bivariate normal with correlation half. Okay, and compose the normal distribution function, capital phi on both, capital phi of x and capital phi of y. Now both the marginals will be uniform. Now we can't quite claim that the correlation between the phi x and phi y will be half, but they will be correlated, correlation may not be half, but they will be correlated. You can actually then theoretically compute the exact correlation and so on. But so this method of we constructed a bivariate distribution, both its marginal are uniform, and it has some other desirable properties. Namely, we thought we wanted correlation to be half, it may be close to half. And this may be a better model than the other one which I told you, which is independent with probability half and identical with probability half. For any realistic modeling, we can agree that this may be, more often than not, this is more appropriate than the other one. Well, this is exactly what is a copula. A bivariate copula is simply a bivariate distribution function. Both marginals should be uniform, that's it. So copula in two dimension or a bivariate copula is simply a bivariate distribution function. Both marginals are uniform. And what I initially started out with, these were the two extreme copulas, one where both are equal, that is one extreme, and the other extreme is both are independent. They both will also give rise to copula. Their joint distribution will still be something where both marginals are uniform. But these two are extreme cases, and the one which we constructed out of bivariate normal is what is called a Gaussian copula. So, some of these first few slides we have already gone over in the morning lecture. Once I knew how much time I had, I just elaborated on the first few slides, so I'll just quickly jump over. These are, just for notation, let us remember once again for our later discussion what is exactly we mean by a return. So, yeah. So if I had put up in the morning, but just for recall. So Sn is the price of the stock of the company on the nth day. The return on nth day is Sn minus 1 divided by Sn minus 1. That is the return. Now, those who have not dealt with financial data or never given a thought to it, you may be wondering why not just Sn minus 1 and why I am dividing by Sn minus 1. Okay. So, these days most of you will be aware of exactly what it means to invest in share markets, even if you are not investing, right? I am assuming that now. Suppose someone is, say you are interested in investing in stock market and you hear that yesterday Infosys share went up by 20 rupees and TCS share went up by 30 rupees. Okay. So went up by is the just difference, Sn minus 1. Okay. It went up by, one went up by 20, one went up by 30. From there, can you conclude that those who had invested in TCS actually earned more and those who had invested in Infosys earned less? No, because the base price comes into the picture. How many, if you had invested 10,000 rupees, how many TCS shares you would have, how many Infosys shares you would have? You will need to compute that number and then multiply that number by the difference, 20 and 30 respectively. Right? So 10,000 divided by Sn minus 1, namely the previous day's price, will give you the number of shares you have. Multiplied by the difference, you will get the amount you got on 10,000 rupees. So amount, if you are investing amount alpha, alpha times Rn dash will be the gain or loss by investing in that share. So this is the right quantity to consider and not just Sn minus 1. Okay. So indeed here is also a story that if one goes back and sees Bacalius's writings, I have not read, but I have read accounts of that. The basic mistake Bacalius did was this, that he argued that the difference in stock prices, that is what he thought of as return, and he modeled that as independent and then various other considerations he got to Brownian motion. If only he had realized this simple thing, which is very easy, simple once you, from hindsight, okay, he could have got what later became the Black-Scholes model, namely the geometric Brownian motion. But this journey from Sn minus 1 to this return defined this way, it took nearly 70 years between Bacalius to Black-Scholes. Okay, all right. So our return is Sn minus 1 divided by Sn minus 1. Now, let us note that this Rn dash is, we can divide and subtract 1, Sn by Sn minus 1, which is roughly minus of 1 minus this quantity, which is roughly log of Sn by Sn minus 1. If Sn by Sn minus 1 is close to 0, then this exactly is the log. So, so either you look at Rn dash or you look at Rn, which is the difference of logs. In most interesting situations, this in one day that we are considering, the increase or decrease in a share price is negligible, and from there that both these are roughly the same. Okay. So if you are reading technical literature, you need to first see how they have defined return. It may not matter in most situations, sometimes it may matter. Okay. So as I talked in the morning, the Black-Scholes model assumed that Rn has a normal distribution, and various data sets say that you have in practice you see that this normal underestimates the tail. In fact, one sees deviation of 4 sigma often, whereas in a normal model deviations of 4 sigma are almost non-existent. Deviation from the mean more than 4 times the standard deviation in normal. So normal probability that an observation is bigger than 4 times sigma is extremely small, 1 in 10,000 or less. So that is what we mean, that we have distribution with fatter tails than normal. So what exactly do we mean by fatter tail? So if Z has a normal distribution, say variance 1, then probability that mod Z bigger than T is, how does it decay as T goes to infinity? That is what we mean by tail of the distribution. For T large, and for normal, for T large it can be approximated by some constant times e power minus T square, and this is where it decays very fast. Okay. So if T is 4, T square is 16, and here you have got e power minus 16. And T is 5, then it is e power minus 25, and that is extremely small number. Okay. So this is what we say, that normal distribution, the tail decays very fast. Compared to that, for the exponential or double exponential distribution, also called Laplace distribution, with the density half e power minus mod x, that is the one with scale parameter 1. So for that distribution, the tail decays as e power minus 3. This is also decaying fast, but not as fast as this. And for Cauchy distribution, it very slowly decaying. It decays like 1 over T. So even with T equal to 10, this is only roughly like some constant times 1 over 10. Whereas here it is e power minus 100, here it is e power minus 10. So you can see the relative, how fast or slow the tail is going. So this last is technically called a fat-tailed distribution. Others are T distribution with small degrees of freedom, 2 or 3 degrees of freedom. Pareto distribution, other stable distributions. These are all fat-tailed distributions. Now, since risk depends on the tail of the distribution, while the normal and observed distributions differ the most in the tails, we may see massive underestimation of risk because the difference is in the tail. So it is crucial to choose the correct distribution while computing or estimating risk. Okay. And we talked about value at risk also in the morning, and I explained the sense in which this quantity is for a normal distribution. Why is this quantity called the risk measure in the var sense? Okay. So if you have a normal random variable with mean mu, variance sigma, probability that minus x is more, minus x is the loss, x is the gain, so minus x is the loss. Probability that minus x exceeds v, if you compute, you will get less than 1%. And that is the accepted risk measure. You want to have a bound so that probability that the loss exceeds that is less than given percent, say 1%. Okay. So now in general, now we take away our assumption of distribution. Now if you have just a stock and its stock prices are modeled as S of t is the stock price at day t, then and you have invested at time 0, then we are looking for a value V such that ST minus S0, this will be the loss, less than equal to minus V, loss exceeds minus V is 1%. Then V will be the value at risk by investing in this stock. Okay. Now, in statistics literature, this percentile concept is very well understood. We do define, of course, median and quartile and interquartile range and so on. I am told by my economist friends that economists did not know this connection with percentiles, and initially at least, and they had to spend a lot of time explaining what exactly they mean by VAR. In economics conferences also. So, in statistics, of course, this percentile is a very well understood concept. Okay. So, as was discussed in the morning, one of the difficulties with VAR is not additive. VAR of sum of random variables is not equal to sum of them, and to obtain VAR, if you want, the whole question is that any entity which is investing in the stock market, even individuals, rarely would be investing in one stock. Okay? That is been shown by various results starting with Markowitz that that's not an optimal way to do. You should diversify. Okay? And when you what do you mean by diversify? That means you should invest in several assets. These assets will have correlation, and what you have to do is to compute or to have some handle on value at risk for the portfolio. Okay. So, let us say somebody has invested in equal number of shares of Infosys, TCS, Airtel, take something completely different segment, and some cement company, another automobile company, 5 companies. Okay. The hope is that if one of them is doing badly, the others will balance it out and it will not go down that much. So, we need to now create multivariate models so that we can assess what is the value at risk for this portfolio. Okay. We would have historical data on each of these 5 stocks. Based on that, we can try to generate a multivariate model. And then, based on that multivariate model, we can talk about value at risk for this portfolio. Okay. So, as I mentioned in the morning, according to this Basel II Accord or Basel II Accord, the capital adequacy for a bank, that is how much capital bank should hold in reserve, is determined by VAR of its assets. And accurate measurement of VAR for a basket of assets or a portfolio of assets is extremely important. If you overestimate it, then your capital is lying idle unnecessarily, it could have earned more money. And if you underestimate it, then you are not covering your risk properly and that quantity can go down. Okay. And so the proper risk estimation for a financial entity is extremely important function. So much so that there is so all such entities will have their own internal risk management function. So a team which is going to be doing risk management, and to ensure that they are doing fair job, that entity has to be externally, you may say, audited, or externally somebody else has to come and examine what they do and certify that what they are doing is right. For the overall management, this is an extremely important function. And so currently I am doing such an external audit for an entity which does settlement of transactions across banks, and there is something called overnight money market and foreign exchange dealings, and this entity called Clearing Corporation of India, they act as the middlemen for all these transactions. and they have a risk management function, and I am doing the audit of that risk management function. So it is an extremely important task to ensure that these financial entities, none of them go down, because if any such event completely destabilizes the market. Okay. But you can't say that, you are not sure, so just double the VAR. Then you are covered your back completely, but then you have locked up too much capital. That also is not admissible. So, okay. Now, when considering a portfolio of stocks which are possibly correlated, we need to model RM1, RMN, RM1 and RMN. That is, these are returns on the first stock, return on the mth stock, and so on. And we need a multivariate distribution whose marginals are, say, double exponential. So if we want to model the individual return with a fatter tail than normal, but not like Cauchy, one choice could be double exponential, which we can try. And we have a given correlation matrix. How would we know what is a correlation matrix? Well, we have a historical data, last 2 years data. On that data, we can compute the daily returns, and then from there we can obtain what is the historical correlation matrix. Okay. If we believe that there are no shock event in the recent past, then we can assume that the next few days to come will be like what happened last 2 years, and so the correlation is what we have estimated historically. So, in this, there are two kinds of approaches. One is you try to fit a parametric model and estimate the parameters of that correlation model. And other is non-parametric, where you just take the empirical as your given truth and compute the required quantities from the empirical. As in general in statistics, I mean, neither is superior to the other. It depends on the context and what you are going to use it for, and so on. You can explore, if that is the critical function for your company for which you work, you can explore both the methods, do back testing. If you had used this method, how would this have performed? How would have that performed? And based on that, make a judgment. Okay. So, all right. So, now, typically when we study statistics, we learn the following. When we are dealing with multivariate situation, then we nicely compute the correlation, which now the standard correlation that we do, I am going to keep calling it the Pearson correlation, because I am also going to bring in another correlation coefficient. So Pearson correlation coefficient is what we just call correlation normally. Covariance divided by product of square roots of variances, right? So, or product moment correlation or linear correlation, various such names exist, but let's call it Pearson correlation. Now, perfectly positively correlated random variables may not have correlation 1. So let's say, what do I mean by perfectly positively dependent random variables? Let's take x to be a binomial with some n and p, and take y to be x square. It's an increasing function of x. As x increases, y also increases. This is what we may call perfectly positively dependent random variables. Whenever one increases, so does the other. But you try to compute and see, your correlation is not going to be 1. Because the Pearson correlation is measuring how much the two are linearly related. Okay? It is not measuring dependence, it is measuring linear dependence. Indeed, if x and y are such that they are uniformly distributed on the boundary of the unit circle, okay? So on xy plane you draw a unit circle passing origin as the center and 1 0 0 1 minus 1 0 and 1 0 minus 1 as these 4 points. You just take that, okay, and take the boundary and let x and y, the pair xy, be the uniform distribution on the boundary of the unit circle. Now x and y, they are not positively dependent, but there is a very strong relative. Once you know x, about y only you know the magnitude of y. Only thing you do not know is it positive side or negative side, because as soon as you know x, you know that x square plus y square is 1. So you know y square perfectly. Only the sign of y remains to be determined. So in some sense there is a very strong relation between x and y. You try to compute the correlation between x, y, it will be 0. So when you are taught, in the early courses you are taught again and again that independence gives correlation 0. The other way is not true. Other way is true only if their joint distribution is normal. Okay, so possible values of correlation depend on the marginal distribution of the random variables. Not all values between -1 and 1 are necessarily obtainable. So for normal we know that every value you can construct a joint model, but if I arbitrarily specify one f and one g and I want a bivariate distribution with a arbitrary correlation coefficient that I described, it may not even exist. Okay. So these are some of the drawbacks. Other thing is, correlation is not invariant under transformation of random variables. For example, log x and log y, log is a monotone transformation, they generally will not have same correlation as x and y. Likewise, e power x and e power y will not have the same correlation. Only when you do linear transformations, correlation remains same. Other thing is, correlations are defined only when the variances of the random variables are finite. It is not appropriate to dependence measure for heavy-tailed random variables where variances may be infinite. If x and y both are marginals or Cauchy, the variances don't exist. You can't even talk about their correlation, right? So as we move away from the normal world, or everything in sight looks normal from there, as we move away, we need to move away from the Pearson correlation coefficient. That is the message. In normal world with everything linear transformations, everything depending on each other linearly, nicely, correlation describes the whole story. Here, it doesn't describe the whole story. In some contexts, we may not even be able to talk about correlation. So, we need to bring in what is called Spearman's rank correlation. Okay. This Spearman rank correlation coefficient between two continuous random variables x and y is defined by the following formula. You take fx and gy. As we just discussed before I started, if f is the distribution function of x, then fx has uniform distribution. Likewise, gy will have uniform distribution. You take fx and gy, you take their Pearson correlation coefficient. Call that rho xy. Now, this is an ad hoc definition. I will explain suddenly where did this come from. In fact, when I have not seen any book which will describe this as a definition. It's there hidden in some papers only, because typically Spearman rank correlation is defined only for a sample and not for the underlying bivariate distribution. For a finite sample, so given a random variable xy, if x1, y1, x2, y2, xn, yn is a random sample for xy, and you define rank correlation means, how is it defined? You look at x's, for x1 you look at its rank amongst x1, x2, xn. And likewise for y's, you compute rank of y1 amongst y1, y2, yn, rank of y2 amongst y2, y1, y2, yn, etc. So So separately for first variable you compute their ranks, second variable you compute their ranks, and now you take the correlation between these ranks. That is what is Spearman rank correlation for a sample. From the faces looks like it's not clear to some, or you may not have seen the definition of rank correlation. So okay, for clarity, let A1 denote the rank of x1 amongst x1 to xn. What do we mean? If x1 is the largest, then the rank is n. If x1 is the smallest, rank is 1. If x1 is the third largest, rank is n minus 3. Okay. So, or these days you are all used to handling data. So you put x1, x2, xn in one column. Next column you put 1 to n. These are the indices. Now sort both the columns together, sort it on x values. The transformation of 1 to n you will get will be the ranks. The largest x will correspond to the... Okay, so now, so separately we compute ranks amongst x's and replace x, or corresponding to x we put a1, a2, an. What will be a1, a2, an will be a permutation of 1 to n. Whichever x is the largest corresponding to that will be n, whichever is the smallest corresponding to that will be a 1, and other values will be inserted in between. Likewise, we compute ranks of y amongst themselves, and let's call them b1, b2, bn. Now, the correlation between a1, a2, n, b1, b2, bn, that is what is the Spearman rank correlation. You can go back and look at any elementary statistics book where the rank correlation is defined this way. You compute ranks of the first variable amongst itself, compute ranks of the second variable amongst itself, correlation between ranks is the Spearman rank correlation. Now, what can be shown is that if you, as n increases, this rank correlation in sample will actually converge to the row which I have defined on the previous slide. So in this sense, this quantity is really representing the same concept as we discussed about rank correlation in a finite sample. Okay. So, now, here the Spearman rank correlation has many interesting and nicer properties than the Pearson rank correlation. Namely, if u and v are strictly increasing functions, then for any random variable xy, rho of ux vy will be same as rho xy. It is easy to see in terms of this rank correlation across samples. Okay. If we make any monotone transformation on x's, okay, if x1, if x3 is the largest, then f of x3 will remain largest and the rank will remain same. Okay. So, the monotone transformation of x's do not disturb the ranks, monotone transformations of y's do not disturb its ranks, and therefore it is very clear that rank correlation, sample rank correlation as defined here will not change in when you do monotone transformations. A little bit of more work will be needed to show that the same property is true when we do monotone transformations. It has to do with how f and g get transformed under monotone transformation of x and y. They cancel each other out, you will get the same quantity. Other way to see it here is, let's say x is the exponential random variable, okay, so positive, all right, and f of x is the distribution function composed with x. Now this is something which you can do yourself and convince yourself later. If instead of x we look at x square, then instead of f we'll have to look at the distribution function of x square and compose that with x square, you will get the same uniform. So f of x gives you a uniform random variable. If you take f dash of x square, where f dash is the distribution function of x square, you will get back the same random variable which is the uniform. Not just equality in distribution, it will be exactly the same value. This is something which you can try yourself and verify. Or as I explained here, we can see it through this rank correlation of finite sample case and then the limiting argument. So, what I explained, that the rank correlation coefficient between the Spearman rank correlation coefficient between xy is same as the Spearman rank correlation between ux and ui. So in this sense, it is a very important property which separates this from the Pearson rank correlation. Okay. Now let us come to how do we construct a joint distribution in m dimension where all marginals are, say, double exponential, mean zeros and scale parameter 1 for now, because changing scale and this is very easy. What is more important? We want all rank correlations to be 0.75. Okay. Of course, we know that these conditions do not determine joint distribution uniquely. Only for multivariate normal, means, variances and Pearson correlations determine the distribution uniquely. So right now we do know it is not unique, but we want to get started with some working model of this uncertainty present, that we have got hold of some characteristics of those uncertainties. Marginals, distributions, correlations. Okay. At least let's start with some model. If there are multiple, then we can worry which one to choose, is the approach. Okay. So a theoretician going back 30 years ago would not have been interested in this question, because he will say, this doesn't determine it uniquely, so what? Alright, but a practical statistician, he wants some model with which he can start doing something. Then if it is not unique, he can explore what other parameters are needed which will determine it more closely to the actual data, etc. Alright. So the question is, can we at least construct one such? So here is one answer, and this is closely mimicking what I gave you the answer about uniform with a given correlation. So remember our task is joint distribution m dimensions, marginals double exponential, mean 0 and scale parameter 1, all rank correlations 0.75. So one answer is this. Take x1, x2, xm multivariate normal, mean vector 0, variances equal to 1, and all Pearson correlation equal to 0.75. Okay. We can write down the density, we can write down whatever thing you want, and you can simulate any standard statistics software, in particular R. You can simulate multivariate observations once you give these parameters. All right. Let ui be phi of xi. Phi is the distribution function of standard normal. All of them have standard normal marginals because all of them have mean 0, variance 1. So phi of xi, when you do, you will get uniforms. So u1, u2, um will be uniform. Now all marginal distributions of u equal to this are uniform. Let G denote the distribution function of the exponential distribution, our target distribution that we wanted. Now, take yi equal to G inverse of ui. So just like you composing with distribution function gets you uniform, composing inverse of the distribution function with uniform will give you the required distribution. So, yi equal to G inverse ui will have the required distribution. So this is one method of constructing a joint distribution where we had prescribed the marginals and where we had prescribed the correlations. Only one catch, that, okay, components are clearly not independent. explicit computation of correlations between phi1, yi and yj seems difficult. It can be shown that the Spearman correlation rho ij between yi and yj is 0.73414. And if instead of starting with all these correlations to be 0.75, if we had started with these correlations to be 0.765362, we would have got that the pairwise Spearman correlations would have been 0.75. Okay. So at least we have a recipe for constructing one joint distribution. This construction is flexible enough. All component marginal distributions could have different parameters or could be from different families as long as they are continuous. Also, the correlations need not be same for all pairs, as we will see shortly. Now, in the beginning I described what is a copula in 2 dimensions. It's a joint distribution in 2 dimensions with both marginals uniform. A copula in m dimension is exactly that. A joint distribution in m dimensions such that each marginal is uniform. That's it. So, example we already constructed, if we take x1, x2, xm to be a multivariate normal, mean 0, variance is 1 and any correlation matrix, okay, then if we take phi of xi, you will get the u vector and that u vector will have uniform, each u will be uniform, therefore the joint distribution of this u will be a copula, m dimension copula, and we have a whole lot of them now because for every variance covariance matrix we will have one distribution of u. Okay. So now we have got hold of not just one but a whole range of m dimensional copulas. This copula, or rather the distribution of u, vector u, is called a Gaussian copula because it is derived out of a Gaussian distribution. So what is a Gaussian copula? Gaussian copula is simply you take the Gaussian, you take some multivariate normal distribution and each component you compose with its own distribution function. What you get is a Gaussian copula. In the literature, I see this expression which gives you an explicit relation between rank correlation rho ij between ui uj in terms of the Pearson correlations rij. So interestingly, I have only seen this formula and references to it, I have not seen any derivation. I tried to do my own derivation, I was not successful and I can't locate a source. Huh? I see. So maybe if you remember that, just send it to me through him because what I tried to do was, I tried to do a huge simulation exercise and tried to verify and yes, it does verify. Of course, it is no proof, but at least so okay. And this is invertible, so you can also write Rij in terms of rho ij. So now, if we want to construct a random vector z1, z2, zm in m dimension such that zi has marginal distributions gi assumed to be continuous and the Spearman rank correlation between zi and zj is rho ij, we can proceed as follows. So now we have m distinct distributions, marginals, and we have described some rank correlation matrix. As I explained, not Pearson because if GIs are general, the variances may not even exist. In any case, when we transform, we can't have any handle on the Pearson correlation. So if we want to specify Spearman correlations rho ij, if we have specified, we can proceed as follows. Here is a recipe. X equal to x1, x2, xm have multivariate normal distribution, mean 0, variance covariance matrix sigma ij, where sigma ij is constructed by just inverting that relation earlier. Okay. Let phi is ui be phi of xi, and then zi is gi inverse of ui. Then we'll have that z's will have the required marginals and it will have the required Spearman rank correlation. Here we need to use the fact that the Spearman rank correlation does not change when you do monotone transformations. So this formula will ensure that the Spearman rank correlation between xi is the rho ij. And once the Spearman rank correlations across x's is the matrix rho ij, we transform monotonely x's to u and then transform u to z. The Spearman rank correlation doesn't change and therefore z's will have the required rank correlation. There are some difficulties. If we arbitrarily specify rho ij's and transform each entry by this formula, we may not get a positive definite matrix sigma. Okay. So if our rho matrix is kind of an extreme, some things are very close to 1 minus 1 or 0, things like that, we may not get. So there is no guarantee that this resulting sigma will be a positive definite matrix. So determining conditions so that after this transformation what you get is a positive definite matrix is a tough one. Okay. Only thing is, in practice you are not going to be requiring these rows which are going to be close to 1 minus 1. They are for moderate values, you will not going to have a problem. Okay. And the joint distribution of Z is completely determined by the marginal distributions Gi and the Gaussian copula with Spearman correlation matrix this. Now, this recipe which I described in this last few slides starting from here, how to construct a joint distribution with these given marginals and a given correlation structure, Spearman rank correlation structure. Essentially, this was explained in that paper written in 2000, which got tagged as the formula that killed the Wall Street. Okay. Now, why it is called the formula that it killed the Wall Street is the following. Though in finance literature, some papers, copula and its usage was being written, but this was a paper written by someone with Chinese origin who changed his first name to a Western sounding name. His name is David Z. Xi, the last name. This explained this in a language understood in the finance world. Okay, and this was lapped up by practitioners. Earlier were only theory papers perhaps, but this one was lapped up by practitioners, and they stopped using their inflating by a safety factor, because now they felt that they are doing both. They are incorporating fat tail distribution and they are incorporating correlations. So now there is no need to ad hocly inflate the VAR that they are getting. They thought that everything is now kosher and this is what is giving them a realistic estimate of VAR. What I am going to explain in the few slides that follow is that even this method is underestimating VAR for a certain reason. And that is why the risk being taken was being underestimated now that they had given up this these ad hoc multiplier factors, and that is why this one is being called the formula that killed the Wall Street. Of course, the formula did not kill. Indiscriminate use of the formula without understanding is what killed. Okay. It kind of takes me back to a debate which I had participated as a schoolboy, and the topic of the debate was, is science a boon or ban for the society? And there I had used a line that it's like a knife. In the hands of a doctor it can save a life, and in the hands of a murderer it can take a life. So science by itself is neither good nor bad. It can be used for well-being of the society, or it can be used to create bombs and bomb the hell out of the rest of the world, right? So it's like that. The formula by itself, okay, it's just a formula. If you use it indiscriminately, it is you who is the problem, not the formula. So the fact that this is just one model with these parameters, and it may not be the model that you are looking for, was forgotten. And what is this factor by which I am confidently saying that this is still underestimating the risk? Let's understand that. Okay. So this is exactly, and by the way, when you see it is not only some weird people writing about this. This includes an article in Financial Times. Okay. Okay. So the whole thing comes out is that the culprit in that formula is the use of Gaussian copula. We have got hold of realistic marginal distributions. We have got hold of a realistic correlation structure, but we are still not divorced Gaussian strongly enough. We are at the back of somewhere there is this Gaussian which is still holding. And what is it that is perpetrating, which is killing, which is underestimating the risk? Okay. Let me skip these few things. Okay, I'll go back, but I want to come to this point first. What is it? So let me define a notion what is called tail dependence. Okay. So for a minute, forget copulas. Let's back in the normal world. All right. Suppose x and y bivariate normal, mean 0, variance 1, correlation rho, mod rho less than 1. Okay. Strictly less than 1. It could be 0.99. Strictly less than 1. Now, let xi sub p denote the pth percentile of normal distribution. So the value, so that probability less than equal to xi p is little p. Now, these two statements require a little more tricky proof, but can be proven by anyone with a little, some measure theory. One course in measure theoretic probability, and one can prove these two limit statements. So what is the first statement? It says that probability that y is less than its pth percentile, given that x is less than the corresponding pth percentile, as p goes down to 0, is 0. Likewise, y bigger than xi p, given that x is bigger than xi p, is also 0 as rho p goes to 1. And this even when they are very strongly correlated, even if rho is 0.99. Okay. What this is saying is that their joint normal behavior, when x is going to a tail, it kind of pushes y to the center. It will not drag y to its tail. And let's come back to a realistic, to the stock scenario. When do we see high correlation across two stock return? When they are in the same industry sector, same sector stocks. So once again, let us come to TCS and Infosys, both IT industry stocks. If Trump tightens the screws for H1B, both of their stocks go down. And if he relaxes, both of them go up, they go together in tandem. So this is why they say same sector stock. So some news which is common for that sector will have the same impact on both the stocks, upwards or downwards. Okay. And that is why it is seen that if you pick up two stocks from the same sector, the returns will have high correlation. If you take from two distinct sectors, they may have correlation but may not be that high. Then it only depends on the overall political climate or the economic climate in the country. Whereas same sector stocks are impacted by the specific news about that sector. Now, from here, if let's say we get a news and that Infosys has had a severe fall, people who deal with stock markets, without closing their eyes, they will say TCS ka bhi gira hoga. If not the same quantity, hugely. Because typically for these established companies, big change doesn't really happen with the internal news, it is to do with the sector news. Overall economic climate in the country as well as that sector, conditions affecting that sector. So, in that sense, if one goes down, even if it is strongly related, normal distribution, you see that our model is not capturing that fact, that when one goes down, it drags the other one down. Typically, that is not captured by the normal model, bivariate normal. For those of you who have studied a little more in probability theory and have, for example, looked at this thing called law of iterated logarithm. Okay. There we see that even if you take two independent components, you get the limit thing as a circle and not a square. Bivariate normal, I mean this normal behavior is reflected there. When one goes to an extreme, the other one is dragged to the center. So this is a very loose analogy, but here the proof requires sitting down and writing out various integrals and estimating them. But so these are tail independent. Even if they are strongly correlated, they are tail independent. Whereas for stock market modeling, specifically same sector stocks, we want not only correlated, but we want tail dependence. And when in reality, when one goes down, so does the other, that means the risk gets multiplied. Whereas our model says that if one goes down, the other will not go down. Therefore, risk will be underestimated. So this is the explanation that creating a multivariate model by use of Gaussian copula is still underestimating risk. It is better than using independent components. It is better than using normal marginals, but it is still not going the whole hog. It is still underestimating the risk. Okay, and this is the fact which got missed when they started using that recipe given by David Z coming through the Gaussian copula. So I should have said that, okay, this is for bivariate normal. Now, I have deliberately written it in this form so that if I apply an increasing function to y, the same function will get applied to xi p. So, any joint distribution constructed through Gaussian copula will inherit this property because it is invariant under monotone transformations. So this is a property not just of the Gaussian bivariate normal distribution, but this is actually a property of any joint distribution constructed out of Gaussian copula. And therefore not appropriate for stock market modeling. So here is a very important takeaway for people who want to work with practical data. As a theoretician, I already said that since this does not determine uniquely, theoreticians have lost interest in that problem. But practitioners want a model. Okay, once you get one model, then you see some other ramifications of that model and see whether it is serving your purpose or not, and if not, you explore and find something more, something better. So now we come to a search that, okay, now we are adding one more parameter to our problem. We want to construct a random vector, m dimension, marginal GI, Spearman rank correlation rho ij, and we want that when rho ij is, for pairs ij where rho ij is say bigger than 0.7, 0.8, something like that, they should also be strong tail dependence. Now we add a requirement here. It may still not determine it uniquely, but we are adding a requirement here. Okay. So now let us look at some other examples of copula. Okay. There are not too many, okay, but an important family of copulas is what is called the class of Archimedean copula. Okay. You start with a continuous strictly decreasing convex function phi from 0, 1 to 0 infinity. At 1 it is 0 and at 0 it is infinity. Okay. Strictly decreasing convex, continuous. Such a function is called an Archimedean copula generator, because for every such function phi I am going to produce a copula. Okay. Given such a function phi, let us write C of u1, u2, um to be phi inverse of, and then you take the sum of the phis. It is just a construct. If psi equal to phi inverse is completely monotone, that is, for all k, if you look at the derivatives, they alternate signs. So first one is always negative, second one is always positive, third one is always negative, etc. Then the function is called completely monotone, and if that happens, then this quantity defines a copula. So if we start with a continuous strictly decreasing convex function satisfying these conditions, and such that phi is completely such that its inverse is completely monotone, then the C as defined here gives you a copula. Why? Because you put the upper values of each of these u's, you are going to get zeros, and then phi inverse of phi u1 will be u1, so that we will immediately verify that all the marginals are uniform. The complete monotonicity comes in to verify that this quantity gives you a m-dimensional distribution function. You remember, it has to be, every component it has to be increasing, but there is more conditions for a function to be a m-dimensional distribution function. You have to compute probabilities of various boxes or cuboids, and that they all should be non-negative. That is where this complete monotonicity comes in, and this defines a copula. And for different generators, you get things which have been named. So if you take phi of t to be, so each of these gives you this, each of these phi satisfies the condition I have imposed. And first one gives you a Gumbel copula, second one gives you a Clayton copula, third one gives you a Frank copula. Okay. Now, for bivariate case, you get a whole lot of copulas, and you can look at their, you can map their distribution functions and then pick whatever seems appropriate for your modeling. When you go to multi-dimension, this is a serious drawback, because while we have defined it in multi-dimension, the rank correlation rho ij between ith and jth component is a constant for I not equal to j. So the rank correlation matrix will be identity for the diagonal, and all off-diagonal entries will be constant. In practice, we are unlikely to need such a thing. We will need pairwise correlations to be specified rather than all of them to be the same. So from that point of view, these Archimedean copulas don't give you much leeway. But for bivariate, it gives you a whole lot of host of examples. And by looking at their graphs and various things, you may be able to choose a copula which is appropriate for your domain or your problem. Okay. Now here is another copula which is very important and interesting. I am calling it T copula. So we again start with normal distribution, mean vector 0, variance covariance matrix sigma ij, sigma I is 1. Now let S be a random variable independent of X having a chi-square distribution, n degrees of freedom, but one chi-square random variable, and each of the components you divide by the same square root S by n. So we do not have S1, S2, Sn, we have one S. Okay. Now, what will be the marginal distribution for each yi? If we fix a I, let's say y1. What is y1? y1 is x1 divided by square root of S by n. S is a chi-square with n degrees of freedom. So distribution of y1 will be t with n degrees of freedom, because it is a normal divided by square root of chi-square by n. Likewise, each of the component variables will have a t distribution with n degrees of freedom. So if Hn is the distribution function of t distribution with n degrees of freedom, ui equal to hm yi will have a uniform distribution. Once you have a vector u1, u2, um such that each of them is uniform, what we have got? We have got a copula, because that exactly is our prescription for a copula. A joint distribution with uniform marginals. And the correlations have got distorted somewhat, but they are persisting, but not exactly same. If rho ij is the rank correlation matrix of U, explicit relation between sigma, the Pearson correlation matrix of x1, x2, xm, and gamma is not available to the best of my knowledge. Okay. However, the same can be obtained via a massive simulation effort. And off and on I have toyed with the idea of doing such a thing and then making an R package to have a simulation from a T copula with a given. Currently, all the packages that I know of which gives you simulation from T copula, they require you to specify sigma, whereas from the data you can estimate gamma. You have to dream what sigma should be, then you have a simulation package. But the requirement, the thing should be that from the data you can estimate gamma. Okay. So we can obtain a T copula with n degrees of freedom and the given rank correlation matrix sigma, gamma, and as we know that if n is large, then T is close to normal. So what would happen? This S by n that if n is large, S by n is nearly a constant. So it will be no different from Gaussian copula. Whereas when n is small, T is violently different from normal. So T with 1 or 2 or 3 degrees of freedom, the copula will have a very different behavior than the behavior of a Gaussian copula. So to recap, a joint distribution can be viewed as a combination of marginal distributions and the underlying copula. So any joint distribution can be decomposed into two parts, its marginals and the underlying copula. And this way of modeling it gives you that you can decouple generating models for both the parts. On one hand, you figure out what should be your marginals be, and secondly, you figure out how they should be bound together with each other, and that is the copula part. So going through this approach allows you to separate these two parts, and marginals is much better understood, and you have a much wider choice, lot of literature. So you can choose appropriate marginals, parametric, non-parametric, all that is up to you. Then you have to figure out a copula. And that is where there are a lot of difficulties. I already argued that Gaussian copula for financial modeling is no good. This host of Archimedean copulas, unless you are in the equicorrelated case, they don't give you any answer. So as of now, what I can make out from the literature, T copula is your only choice. And okay. Now I had ruled out Gaussian copula on the count of tail dependence, that a Gaussian copula does not doesn't seem appropriate, because even when the correlations are strong, they are tail independent. Components are tail independent. Now I am formally defining tail dependence for any two random variables. So for a univariate random variable x, let me denote by gamma xp the pth percentile of distribution of x. And for random variables x and y, we can define the lambda L and lambda u, the lower tail dependence and the upper tail dependence, by the same kind of thing which I had done for normal. Conditional probability that y is less than its pth percentile, given that x is less than its pth percentile, limit as p goes to 0, or limit as p goes to 1, the corresponding upper parts. Gamma L xy measures the lower tail dependence, lambda u xy measures the upper tail dependence. And if f and g are increasing functions, we can easily show that the lower or upper tail dependent measures are independent of these monotone transformations. And thus lambda L, lambda u are functions of the underlying copula and not the marginal distributions. Thus if xy is marginals f and g in the underlying copula is Gaussian copula, we will get that lambda L equal to lambda u equal to 0. And that was the reason for our rejection of Gaussian copula. So this is why I had already argued. Now, a better choice seems to be T copula with small degrees of freedom. For a T copula with new degrees of freedom, with Pearson correlation R for the underlying normal, one has, this is the explicit formula for the tail dependence measure of the T copula, which is lambda L equal to lambda u equal to 2h nu plus 1, some argument where h nu is the distribution function of the T distribution with new degrees of freedom. And even if R is 0, there is some tail dependence. And that is coming because even the x components are independent, but you are dividing them by the same chi-square, and that is where the dependence is coming. Okay. So, this is only an unfinished story. There is no final answer in this story yet. Okay. So maybe we start using T copula and we find some other property which is not appropriate till we look at some other property. Okay. One thing let me mention that because of inherent symmetries we get for T copula, that the lower tail dependence coefficient is the same as the upper tail coefficient. Whereas you talk to the practitioners and in stock market, the lower should be higher than the upper. Upper could even be 0. If TCS goes up much, Infosys may or may not go up, but if TCS goes down, Infosys will go down and vice versa. So, same sector stocks, the lower tail dependence should be a lot more than the upper tail dependence, whereas the T copula is giving us both of them to be equal. So, T equal to 1 or 2 degrees of freedom would be better than Gaussian copula, and as I said just now, they are equal, but in practice one would like lambda L to be significantly bigger than lambda U. So, we had seen that using Gaussian distribution when the assets have fatter tail results in Gaussian copula, it still results in underestimation. Now, here is from one source I have compiled, taken this one. So, these are, this print is small, so let me read the legend above. Joint quantile exceedance probabilities for bivariate Gauss and T copulas with correlation parameters 0.5 and 0.7 respectively. For Gauss copulas, the probability of joint quantile exceedance is given. For T copula, the factors by which this must be multiplied is given. Okay. So, joint exceedance is probability that X is less than the corresponding this quantile and Y is less than the same quantile, joint probability. So, for normal 0.05 is, if I am not mistaken, 1.64 or minus 1.64. So, probability X less than 1.64, minus 1.64, Y less than minus 1.64. When their correlation is half, for Gauss, for Gaussian copula, this probability is 1.21 times 10 to the power minus 2. For T copulas with 8, 4 and 3 degrees of freedom, what we get is the factor by which this should be multiplied, and the factors are going from 1.2 to 1.5. So, if you go down to 3 degrees of freedom for the underlying copula, your multiplier is 1.5. So, there is quite a bit of difference, and we have two things for rho equal to 0.5, 0.7, the same things are given. As you go more to the tail from 0.05 to 0.01, then 0.005, then 0.0001, the multiplying factors keep increasing. So, if you are interested in the extreme tail by using the Gaussian copula rather than a T copula with 3 degrees of freedom, you may be making an error of by the order of magnitude of 5.8. Okay. So, here is the effect of the dimension. Now they are fixing, you are fixing 1% quantile exceedance probabilities. Okay, so, this one only we are considering. This was a 2-dimension case. Now we fix the 1% quantile exceedance probabilities, but now we increase the dimension, and now from dimension 2 to 5, if you go even for 1%, the multiplying factor has gone from 2.55 to 10.34, even in 5 dimensions. And in stock market context, people are working with hundreds and thousands of dimensions, and that shows the huge factor by which they could be underestimating risk if you just use the Gaussian copula. Okay. So, I think this is the last slide. So, the upshot of what I said in this 1.5 hours or 1 hour 20 minutes till now. One, we discussed the notion of copula and a way of generating multivariate models through specifying a copula and through marginal distributions. Copulas, Gaussian and T copulas, we have wide variety of choice. Equicorrelated copulas, we can have even wider choices. Gaussian copula, the tail dependence is 0, and even when the correlations are high across the components, and that's why not appropriate for modeling stock market. Doesn't mean it is not appropriate for modeling other distributions or other phenomena. Okay? So it's not that Gaussian copulas are no good, no. But for finance modeling, they are not appropriate, for sure. Okay? T copulas, better than Gaussian, more appropriate than Gaussian, but still there is something not so good about it, namely the upper and lower tail dependence coefficients are the same, which is not exactly what we should be looking for. Few things which are not said in these slides. Okay, we have created a model, but then you want answers to some questions. For example, you generate some test. How do you get hold of the critical region for that test? Where will you get the cutoff? How typically you do that by getting hold of the distribution of the relevant quantity, and then using that you get the test cutoff. Now here, one thing is that once you go through a joint distribution doing via copula, more or less closed forms answers for any problem, any question is out. Okay. So if you do a test based on this, is it unbiased, is it not, what is its efficiency? You do a test based on this, what should be the cutoff, what is its power? All these questions, you cannot get a closed form answer. But you can resort to simulation. All the answers that you want can be done via simulation, which is one of the reasons why, though copula as a notion came into the literature in the 60s, even in the 70s and in 80s, perhaps 90s, it was not being taught, because simulation had not yet become a way of doing computing or doing statistical computations. Computing power was increasing, but still people were not comfortable, blah, blah, blah. When I was a student, not available. Later, even if available, statisticians were not using it. By 95 to 2000, computing power had come to everybody's desktop, and from then on, usage of copulas in modeling, at least in finance industry, it has taken off in a big way. After the Lehman Brothers crisis, maybe they have moved away from Gaussian and now using T copulas till the next crisis hits them, and then they will discover some new copula. Off and on, I have tried to do some other transformations and see if I can come up with some copula where lambda L is bigger than lambda U. Till now, I have had no success. Okay. Doing computations via simulation here is easy because of the way I have described things. It is actually easier to simulate than to prove mathematically anything. Because let me go back to this one. How do we generate observations? For T copula, how do we generate the U's in the T copula? Well, you can simulate a multivariate normal once you have described sigma. Do these transformations. So now you have got her simulated values from that copula, and compose it with the required G, and you have got a sample from your Z's that you are looking for. Okay. So the way of this, I have described this construction is ready-made for writing a simulation routine to simulate from the joint distribution that you have specified via marginals and copulas. Absolutely ready-made. You can't compute quantities related to that. That's a different matter. Okay. Also, as yet, I have not seen much use of copulas in modeling other than in finance domain. In fact, if I go back 10 years, around 2007-8, if I tried to search with the word copula, all the hits in Google I would get were from some finance journals. Now it has improved, now I do get other hits. But 10 years ago, everything was from finance domain. Now others are writing about it, but usage as far as I can make out is still in finance domain. So let me stop here and we have some time for questions if you have. Both these presentations are here. People can anyone who wants them can copy it from the desktop and